Hello sir, I am Astha Singhada from Chemical Second Year. My topic is Basic Introduction to Heat Transfer. In this, I will explain basics of heat transfer, what is heat transfer, different mode of heat transfer, etc. Let's first talk about heat and heat energy. Heat is a form of energy, and energy is defined as the ability or capacity to do work on some form of matter. Heat energy is the kinetic energy due to motion of atoms and molecules. Heat energy is created by the movement of particles that produces heat. Heat energy increases as temperature increases because as temperature increases, atoms move faster. There are several forms of energy including the following. Potential energy. Potential energy is the energy which a body possesses as a consequence of its position in a gravitational field. Kinetic energy. Kinetic energy is the energy which a body possesses as a consequence of its motion. That is, for example, wind blowing across a wind generator. It is dependent upon an object's mass and velocity. Internal energy. Internal energy is the total energy, potential and kinetic, stored in molecules. Heat or thermal energy. Heat energy is kinetic energy due to motion of atoms and molecules. It is energy that is in the process of being transferred from one object to another because of their temperature difference. Radiant energy. Radiant energy is the energy that propagates through the space and through material media in the form of electromagnetic radiation. Heat transfer. Heat transfer is a process by which internal energy from one substance transfers to another substance. The driving force for heat transfer is temperature difference. Heat transfer cannot be measured directly, but the temperature difference can be measured, and with the help of temperature difference, we can measure amount of heat transfer. Thermodynamics is the study of heat transfer and the changes that result from it. An understanding of heat transfer is crucial to analyzing a thermodynamic process, such as those that take place in heat engines and heat pumps. Unit of heat transfer that we use: SI unit joule, MKS unit calorie, rate of transfer of heat kilowatt. Forms of heat transfer. Under the kinetic theory, the internal energy of a substance is generated from the motion of individual atoms or molecules. Heat energy is a form of energy which transfers this energy from one body or system to another. This heat transfer can take place in a number of ways. The three of them are given here. These three are the main modes of heat transfer. First one, conduction. Conduction is when heat flows through a heated solid through a heat current moving through the material. You can observe conduction when heating a stove burner element or a bar of metal which goes from red hot to white hot. Second one, convection. Convection is when heated particles transfer heat to another substance, such as cooking something in boiling water. Radiation. Radiation is when heat is transferred through electromagnetic waves, such as from the sun. Radiation can transfer heat through empty space, while the other two methods require some form of matter on matter contact for the transfer. As you can see in this picture, water is boiling in a container. The handle of the container is heated up at one end of the side. And then due to conduction, heat is transferred to other end and the hand shown here feels hot. This is the other end. This one is the red hot area and this one is the white area. The direction of conduction is from here to here. We can see that the burner and the container are in matter-on-matter contact with each other. Here, the heat transfer is through convection, as you can see here, the boiling water. This burner also radiate heat energy which is transferred through radiation, and you can see here. In order for two substances to affect each other, they must be in a thermal contact with each other. If you leave your oven open while turned on and stand several feet in front of it, you are in thermal contact with the oven and can feel the heat it transfers to you by convection through the air. Normally, of course, you do not feel the heat from oven when you are several feet away, and that is because the oven has thermal insulation to keep the heat inside of it, thus preventing thermal contact with the outside of the oven. This is of course not perfect, so if you stand nearby, you do feel some heat from the oven. Thermal equilibrium. Thermal equilibrium is when two items that are in thermal contact no longer transfer heat between them. Now, effect of heat transfer. The basic effect of heat transfer is that the particles of one substance collide with the particles of another substance. The more energetic substance will typically lose internal energy, that is cool down, while the less energetic substance will gain internal energy, that is heat up. The most blatant effect of this in our day to day life is a phase transition, where a substance changes from one state of matter to another, such as ice melting from solid to a liquid as it absorbs heat. The water contains more internal energy, that is, water molecules are moving fast around faster than in the ice. In addition, many substances go through either thermal expansion or thermal contraction as they gain and lose internal energy. Water and other liquids often expands as it freezes, which anyone who has put a drink with a cup in the freezer for too long has discovered. Heat capacity. The heat capacity of an object helps define how the object's temperature responds to absorbing or transmitting heat. Heat capacity is defined as the change in heat divided by the change in temperature. Laws of thermodynamics. Heat transfer is guided by some basic principles which have become known as the laws of thermodynamics, which define how heat transfer relates to work done by a system and place some limitations on what it is possible for a system to achieve. Now let's talk about the difference between thermodynamics and heat transfer. Thermodynamics tells us how much heat is transferred, that is dq, how much work is done, that is dw, and final state of the system. Whereas heat transfer tells us how with what mode dq, that is heat, is transferred, at what rate dq is transferred, and temperature distribution inside the body. Difference between heat and temperature. In heat transfer problems, we often interchangeably use the term heat and temperature. Actually, there is a distinct difference between two. Temperature is a measure of amount of energy possessed by the molecule of a substance. It manifests itself as a degree of hotness and can be used to predict the direction of heat transfer. The usual symbol for temperature is capital T. The scales for measuring temperature in SI units are the Celsius and Kelvin temperature scales. Heat, on the other hand, is energy in transit. Spontaneously, heat flows from a hotter body to a colder one. The usual symbol for heat is Q. In the SI system, common units for measuring heat are the joule and calorie. Heat transfer mechanism. Heat, the form of energy that can be transferred from one substance to another as a result of temperature difference. Thermodynamics is concerned with the amount of heat transfer as a system undergoes a process from one equilibrium state to another. Heat transfer deals with the determination of rate of such energy transfers as well as variation of temperature. The transfer of energy as heat is always from the higher temperature medium to the lower temperature one. Heat transfer stops when the two medium reach the same temperature. Heat can be measured, sorry, Heat can be transferred in three different modes: conduction, convection, and radiation. All the mode of heat transfer require the existence of a temperature difference. Now let's talk about why should we know about heat transfer. Heat transfer is required to know because it tells us about the heat transfer rate so we can calculate the time taken by a system to change in a specified temperature. Example, by knowing about the heat transfer, we can calculate in how much time a cup of tea, which is initially at 60 degrees Celsius, takes to cool to 20 degrees Celsius. Heat transfer widely used in automobile for cooling of IC engines. It is widely used in production of electronic equipment such as computer, DVD player, TV, etc. It is used in various power plants such as boiler, condenser, steam developer, refrigerator, etc. Applications of heat transfer. Heat transfer is the study of flow of heat. In chemical engineering, we have to know how to predict rate of heat transfer in a variety of process situations. For example, in the production and use of process steam, which is brought to various locations in a plant through a steam pipe as a heating utility also, these steam pipes need to be insulated to minimize heat loss to the ambient air. Such insulation is also important when transporting hot fluid from one place to another. A similar application is the transport of refrigerated liquid through piping. Here we need to insulate to avoid transferring heat into the liquid from the ambient air. Chemical reactors can generate heat if the reaction is exothermic, and this heat must be removed to avoid a runaway reaction. Likewise, endothermic reactions need a supply of heat to maintain the reaction. Heat transfer is Heat transfer also is important in our daily lives. For example, we heat our homes in the winter using hot water in baseboard heater. We boil water routinely for cooking purposes. If you look inside a modern personal computer, you will see a fan that is used to cool the electrical circuitry, which becomes warm because of the flow of electrical currents through resistances. Sometimes, when the circuits are dense, a refrigerant is used in a sealed tube that is boiled at one end where it is warm to take away the heat and condensed at the other end where it is cooler. The bodies of warm blooded animals contain many examples of internal heat transfer as well as heat transfer with the surrounding air. Such animals possesses a finely tuned system that regulates their body temperature by adjusting rates of internal reactions to produce heat, varying blood flow rates as needed, and varying the diameter of blood vessels. Finally, life on Earth is possible only because of energy received from the sun by radiative heat transfer. Radiative heat transfer also is important in the manufacture of steel and other such materials and in furnace used for melting glass. In all of these situations and many others, we can identify three basic mechanisms of heat transfer. They are conduction, convection, and radiation. Now we will look into these three modes of heat transfer in detail. The first one is conduction. The transfer of energy from the more energetic particles of a substance to the adjacent less energetic ones is a result of interaction between the particles. In gases and liquids, Conduction is due to the collision and diffusion of molecules during their random motion. In solids, it is due to the combination of vibrations of the molecules in a lattice and the energy transport by free electrons. The rate of heat conduction through a plane layer is proportional to the temperature difference across the layer and the transfer and the heat transfer area, but is inversely proportional to the thickness of the layer. Rate of heat conduction is directly proportional to the area into the temperature difference and inversely proportional to the thickness. That is, rate of heat transfer for conduction is equals to K into A T1 minus T2 upon delta X is equals to minus of Ka delta T upon delta X. Unit of rate of heat transfer of conduction is watt. The conductive heat transfer rate can be measured with the help of Fourier law of heat conduction. For understanding of this law, let us assume a wall which is maintained at temperature T1 at one side and temperature T2 at other side. The thickness of the wall is delta X and the effective surface area for heat transfer is A. Now applying Fourier law for heat conduction on this wall, Q is equals to minus Ka delta T upon delta X. Here T1 is the higher temperature and T2 is the lower temperature. And we know heat is transferred from higher temperature to lower temperature. So heat will transfer in this direction. And we have to calculate the rate of heat transfer. When X tends to 0, follow laws of heat conduction. Thermal conductivity K, a measure of ability of a material to conduct heat. Temperature gradient dt by dx, the slope of temperature curve on a Tx diagram. Heat is conducted in the direction of decreasing temperature and the temperature gradient becomes negative when temperature decreases with increasing x. The negative sign in the equation ensures that heat transfer in the positive x direction is a positive quantity. The rate of heat conduction through a solid is directly proportional to its thermal conductivity. In heat conduction analysis, A represents the area normal to the direction of heat transfer. The rate of heat transfer is directly proportional to the temperature gradient, that is dt by dx. Conduction equation. The coefficient of thermal conductivity shows that a metal body conducts heat better when it comes to conduction. The rate of conduction can be calculated by the following equation. Q equals to K into A T hot minus T cold upon D, where Q is the transfer of heat per unit time, A is the thermal conductivity of body, A is the area of heat transfer, T hot is the temperature of hot region, T cold is the temperature of cold region, and D is the thickness of body. Fourier law. It states that the rate of heat transfer is proportional to the temperature gradient exists and the surface area of the material. It is known that the conduction of heat takes place when the molecules of matter vibrates or agitate and transmit energy to the adjacent molecule. As the neighboring molecule collide, heat energy is transferred from a higher temperature area to a lower one. This process abides Fourier law. So let us go through the Fourier law. Fourier law of thermal conduction states that the rate of heat transfer through a material is proportional to the negative gradient in the temperature and the area perpendicular to the gradient of the surface through which the heat flows. Process of heat transfer are measurable in the form of rate equation. The rate equation for conduction or mode of transfer is deduced based on Fourier law of thermal conduction. It says that the rate of transfer of heat across a substance is directly proportional to the negative gradient in the temperature and area. To find the solution of Fourier law, the relationship of geometry, temperature difference and thermal conductivity of material is derived. Joseph Fourier first introduced this law in the year 1822 and concluded the heat flux resulting from thermal conduction is proportional to the magnitude of the temperature gradient and opposite to it in sign. Heat flux. Heat flux is the heat transfer rate per unit area normal to the direction of heat transfer. It can also be referred to as heat flux density. Since it is a vector quantity, it has both magnitude and direction. Examples of conduction. Heat transfer by the lower surface of a pan to the upper surface which is placed on a burner. Conduction may occur in solid, liquid and gases. In solid, it is due to the flow of electron and lattice molecules vibration. And in liquid and gases by the collision of molecules and transfer of energy and momentum from one molecule to another. Conduction is higher in solid and lower in liquid and gases. The relation between the heat transfer rate with temperature difference and surface area is established by the Fourier, known as Fourier law of conduction. Ironing of clothes is an example of conduction where the heat is conducted from the iron to clothes. It is transferred from hand to ice cube, resulting in melting of an ice cube when it held in hands. Heat conduction through the sand at the beaches. This can be experienced during summer. Sand is a good conductor of heat. Assumptions of Fourier law. Steady state conduction. Temperature does not change with time. Unidirectional heat flow. Constant temperature gradient and linear temperature profile. No internal heat generation. Bounding surfaces are isothermal in character. Isotropic and homogeneous material. Now let's talk about thermal conductivity. The rate of heat transfer through a unit thickness of material per unit area per unit temperature difference. Thermal conductivity of a material is a measure of ability of material to conduct heat. A high value for thermal conductivity indicates that the material is a good heat conductor, and a low value indicates that the material is a poor heat conductor or insulator. Here is a sample experimental setup to determine the thermal conductivity of material. The range of thermal conductivity of various materials at room temperature. The gas, molecular collision, molecular diffusion. Liquid, molecular collision, molecular diffusion. Solid, lattice vibration, flow of free electrons. This is the mechanism of heat conduction in different phases of substances. The thermal conductivities of gas such as air vary by a factor of 10 to the power 4 from those of pure metal such as copper. Pure crystal and metal have the highest thermal conductivities and gases and insulating materials the lowest. The variation thermal conductivity of various solid liquid gas with temperature. Now, the second mode of heat transfer is convection. Convection is defined as the movement of fluid molecules from higher temperature region to lower temperature region. The mode of energy transfer between a solid surface and the adjacent liquid or gas that is in motion, and it involves the combined effect of conduction and fluid motion. The faster the fluid motion, the greater the convection heat transfer. In the absence of any bulk fluid motion, heat transfer between a solid surface and the adjacent fluid is by pure conduction. Heat transfer from a hot surface to air by convection. Convection is the combined effect of heat transfer by conduction as well as fluid flow, but it is highly dependent upon the fluid flow rate, so it is defined as a separate mode of heat transfer. Forced convection. If the fluid is forced to flow over the surface by external means such as a fan, pump, or the wind, natural or free convection. If the fluid motion is caused by buoyancy force that are induced by density difference due to the variation of temperature in the fluid. Heat transfer processes that involves heat transfer processes that involve change of phase of a fluid are also considered to be convection because of the fluid motion induced during the process, such as the rise of the vapor bubbles during boiling or the fall of the liquid droplets during conduction. This is the example of forced convection and natural convection. Here, the hot egg is automatically cooled by the natural air present in the atmosphere. But here, the hot egg is cooled by the use of artificial means, that is the fan, not all by the atmosphere. So this is the forced convection and this is the natural convection. A cooling of a boiled egg by forced and natural convection, this is the example. Convection equation. Convection heat transfer is explained by Newton's law of cooling. So, Newton's law of cooling, it states that the rate of heat transfer is proportional to the surface area of the body and the temperature difference exists. Q is equals to H into A T2 minus T1, where H is known as convection heat transfer coefficient and A is the surface area and Q is the heat transfer rate. As the temperature of liquid increases, the liquid's volume also has to increase by the same factor, and this effect is known as displacement. The equation to calculate the rate of convection is as follows: Q equals to Hc into A Ts minus Tf, where Q is the heat transfer per unit time, H is the coefficient of convective heat transfer, A is the area of heat transfer, Ts is the surface temperature, and Tf is the fluid temperature. The value of H depends upon the following factors: surface condition, roughness and cleanliness, geometry and orientation of the surface, plate, cylinder or sphere placed vertically or horizontally, thermophysical properties of the fluid, that is density, viscosity, specific heat, thermal conductivity, etc. Nature of fluid flow, that is laminar or turbulent, boundary layer configuration, prevailing temperature condition. Newton's law of cooling. Now let's discuss about this law. The temperature difference in any situation results from energy flow into the system or energy flow from the system to the surrounding. Newton's law of cooling explains how the temperature of a body relates to its time of cooling. It is named after the famous physicist Sir Isaac Newton. Principle. According to Newton's law of cooling, the rate of cooling of a hot body is directly proportional to the temperature difference between the body and its surrounding. Convection heat transfer coefficient, that is watt per meter square degree Celsius. This is the unit. As the surface area through which convection heat transfer takes place Ts, the surface temperature, T infinity, the temperature of the fluid sufficiently far from the surface. The convection heat transfer coefficient H is not a property of fluid. It is an experimentally determined parameter whose value depends on all the variables influencing convection, such as the surface geometry, the nature of fluid motion, the properties of fluid, the bulk fluid velocity. This is the example of heat transfer from a hot surface to air by convection. Convection examples: boiling of water, that is, molecules that are denser move at the bottom, while the molecules which are less dense move upward, resulting in circular motion of the molecules so that water gets heated. Warm water around the equator moves towards the pole, while cooler water at the poles moves toward the equator. Blood circulation in warm blooded animals takes place with the help of convection, thereby regulating the body temperature. It is the heat transfer between a solid surface and adjacent layers of liquid or gas which are in motion. Convection is highly depends upon the velocity of fluid, so it is subdivided into two parts. Forced convection, when fluid is forced toward the solid surface. Free convection or natural convection, when fluid is free to move or fluid is followed by virtue of density difference. The relation between convection heat transfer and the surface area of the body and temperature difference is given by Newton, known as Newton's law of cooling. Here, as you can see, the coffee mug, the temperature of coffee mug is 60 degrees centigrade and the outside temperature is 40 degrees centigrade. So the rate of heat transfer, so the direction of heat transfer will be from 60 degree to 40 degree. Now the third mode of heat transfer is radiation. Thermal energy transferred by radiation is caused by electromagnetic waves or photons. Thermal radiation is emitted by all surfaces which are kept at a finite temperature level. This happens from solid, liquid and gases. Rate of emission increases with temperature level. Radiant energy does not require a material medium for its transport. Moreover, radiation transfer will occur effectively in vacuum. Radiation is another form of heat transfer. It does not require any medium and can be used for transfer of heat in a vacuum as well. This method uses electromagnetic waves which transfer heat from one place to another. The heat and light from the sun in our solar system reach our planet using radiation only. In fact, radiation is the most potent method of heat transfer. In winters, when we sit near a fire, we feel warm without actually touching the burning wood. This is possibly by radiation only. Thermal radiation is generated by the emission of electromagnetic waves. These waves carry away the energy from the emitting body. Radiation takes place through a vacuum and or transparent medium which can be either solid or liquid. Thermal radiation is the result of random motion of molecules in the matter. The movement of charged electrons and protons is responsible for the emission of electromagnetic radiation. The energy emitted by matter in the form of electromagnetic waves or photons as a result of the changes in the electronic configuration of the atom or molecules. Unlike conduction and convection, the transfer of heat by radiation does not require the presence of an intervening medium. In fact, heat transfer by radiation is fastest at the speed of light and it suffers no attenuation in the vacuum. This is how the energy of the sun reaches the earth. The heat transfer studies, we are interested in thermal radiation, which is the form of radiation emitted by bodies because of their temperature. All bodies at a temperature above absolute zero emit thermal radiation. Radiation is a volumetric phenomena and all solid, liquid and gases emit, absorb or transmit radiation to varying degrees. However, radiation is usually considered to be a surface phenomena for solids. The mechanism of heat flow by radiation consists three distinct phases. Conservation of thermal energy of the hot source into electromagnetic waves, that is, photons are propagated through the space as rays. Second, passage of wave motion through intervening space. Photons travel with unchanged frequency in straight path with speed equal to that of light. Transportation of wave into heat. Reconservation of wave motion into energy occurs in the receiving surface, which may partly absorb, reflect, or transmitted through. Radiation equation. As temperature rises, the wavelength in the spectra of radiation emitted decreases and shorter wavelength radiation are emitted. Thermal radiation can be calculated by Stefan-Boltzmann law. This is given here, where P is the net power of radiation, A is the area of radiation, Tr is the radiator temperature, T is the surrounding temperature, and E is the emissivity, and this is the Stefan's constant. In radiation, we use the term black body. A black body is an idealized physical body that absorbs all incident electromagnetic radiation regardless of frequency or angle of incidence. The name black body is given because it absorbs radiation in all frequency, not because it only absorbs. A black body can emit black body radiation. On the contrary, a white body is the one with a rough surface that reflects all incident rays completely and uniformly in all directions. A black body in thermal equilibrium, that is at constant temperature, emit electromagnetic black body radiation. The radiation is emitted according to Planck's law, meaning that has a spectrum that is determined by the temperature alone, not by the body's shape or composition. An ideal black body in thermal equilibrium has two notable properties. First, it is an ideal emitter. Every frequency it emits as much or more thermal radiative energy as any other body at the same temperature. Second, it is a diffuser emitter measured per unit area perpendicular to the direction the energy is radiated isotropically independent of direction. Radiation examples. Microwave radiation emitted in the oven is an example of radiation. UV rays coming from the sun is an example of radiation. The release of alpha particles during the decaying of Uranium 238 into thorium 234 is an example of radiation. The basic rate equation for radiation at heat transfer is the Stefan-Boltzmann law. Stefan-Boltzmann law statement that the total radiant heat power emitted from a surface is proportional to the fourth power of its absolute temperature. Formulated in 1979 by Austrian physicist Joseph Stefan as a result of his experimental studies. The same law was derived in 1884 by Austrian physicist Ludwig Boltzmann from thermodynamic consideration. If E is the radiant heat energy emitted from a unit area in 1 second, that is the power from a unit area, and T is the absolute temperature in Kelvin, then E is equals to sigma T to the power 4. Here, the Greek letter sigma representing the constant of proportionality called the Stefan-Boltzmann constant. This constant has value 5.67 into 10 to the power minus 8 watt per meter square per Kelvin to the power 4. The law applies only to black bodies, theoretical surfaces that absorb all incident heat radiation. The Stefan-Boltzmann law, also known as Stefan's law, is a law that expresses the total power unit surface area, otherwise known as the intensity, that is radiated by an object, often taken to be a black body. The formula used to determine at what wavelength the power peaks at is Wavin law. The Stefan-Boltzmann law explains how much power the sun gives off given its temperature, or allows scientists to figure out how hot the sun is based on how much power strikes the earth in a square meter. The law also predicts how much heat the earth radiates into space. The Stefan-Boltzmann law doesn't say anything about the wavelength of light emitted, that is described by the Planck's radiation formula. This law is expressed as this: the total radiated energy increases as temperature is increased. Based on common observation, wherein a heated object glows brighter as temperature increases, it should not be too surprising that objects radiate more energy with an increase in temperature. As well, by manipulating the Stefan-Boltzmann equation, the temperature of Earth without the greenhouse effect can be determined when values of power from sun and surface area of Earth are used, where EB is the energy radiated per unit time, T is the absolute temperature of the surface, and this is the Stefan-Boltzmann constant. Its value is 5.67 into 10 to the power minus 8 watt per meter square Kelvin की power 4. The idealized surface that emit radiation at the maximum rate. Black body radiation represents the maximum amount of radiation that can be emitted from a surface at a specified temperature. Emissivity, a measure of how closely a surface approximates a black body, for which tau is equals to 1 of the surface. Emissivity lies between 0 to 1. Radiation emitted by real surface. Now again see some examples of radiation. Heat transfer from sun to earth. Radiation occurs by electromagnetic waves which propagate at the speed of light. It is the fastest medium of heat transfer among all. The relation between heat transfer rate, surface area, and temperature difference is given by Stefan Boltzmann, known as Stefan Boltzmann law. So this was all about basic introduction to heat transfer. In this we discussed about heat energy, different forms of energy, heat transfer, modes of heat transfer, temperature, thermodynamics, the different modes of heat transfer like conduction, convection, radiation. In convection we saw the convection equation, its examples, Fourier law. In convection we studied the convection equation, its examples, and Newton's law of cooling. In radiation we study about what is radiation, equation, Stefan Boltzmann law, and examples of radiation. We studied that the direction of heat transfer is from higher temperature to lower temperature, that is from hotter body to a colder body. So that's all from my presentation. Thank you.